let's we dig a little bit further into the world of fraud. So we heard about any kind of statistical errors and some fraud. Indeed, it's time now to go a little bit deeper in what fraud in biomedical publishing is. The fact is that if you look to statistics, so to the frauds that were reported and solved by Office for Research Integrity in the US, you discover that there is one special kind of data manipulation which is rising, which is image manipulation. Already in 2008, 70% of fraud cases which were declared fraud by Office for Research Integrity in US were due and involve some form of image manipulation. Everything started with digital image manipulation, which is the subject of my talk now. So how many fraud cases involving image manipulation do you have? People started checking for this. This is an analysis by Morten Oxvold. He examined 200 papers, roughly 200 papers in basic oncology by hand, by checking images one by one, and he discovered around 1/4 of papers to contain different sort of manipulation in images. Some were very serious, some were tiny, but anyway they were considered misconduct. There is a larger analysis now available by Elizabeth Bick. For several years, she and some student of her group ran a manual analysis of more than 20,000 papers from different journals, and they found that depending on the journal and on the topic, they found between 0.3% and roughly 12% of papers to contain at least one manipulated image. The thing is that image fraud and image manipulation for scientific publication is becoming an industry. That's because papers are out for sales, like Nature reported in several editorials, and so there are companies, for example in China, which hack software like this one. This is MacVector. This software is, for example, able to produce photorealistic gels. So you simply design an experiment on the left, and it produces for you a photorealistic gel. And the good thing is that you can have also the address of this Chinese company, which went one step further by introducing a further noise introduction and slight deformation of the gel so that it looked like a perfect image for publications. And in a collaboration with some Chinese researchers, we could spot hundreds of these gels which were already either published or in, let's say, prepared papers for publications. What you can do, you can fight back, building on the fact that the image is digital. So if digital manipulation is possible, it's also possible digital analytics of images. This is what we do. So you will have false positives by the software, papers that should not be flagged, basically, and also false negatives. That means papers that you will miss. They contain a fraud, but you will miss it. This is the cost to have an automated analysis. The advantage is that you pass from millions of papers to a few thousand and then to a few hundreds of papers. So that in next steps, a human analyst can use software tools to study the finding of the software and see whether there is indeed a fraud or not. And in the end, of course, you produce a report, and then all the process that you already saw with what David was showing to you started. So the legal part, the journal contacting part, the university contacting part. So if you're lucky, in my experience, in maybe 1% of the cases, in the end you get literature fixed, corrected, or a paper retracted. This is due to several obstacles, which are legal, which are due to the editorial policies, mostly to editorial policies which are imposed by the publisher, not by the editorial committee itself. Even people which are bound to copy, they do commit violation of their own regulations. But anyway, so we had two pipelines in place for the automatic step. One pipeline is aimed to find internal duplication. So you want to find whether a given image, which represent some physical experiments like gel electrophoresis experiments or whatever, microscope image, do contain self-similar regions. Because very often what people manipulating image do is to simply copy, like you saw in some gel by David. They copy, for example, one band, they duplicate it in the same image. Or they copy some cells, of course, they stretch, rotate, manipulate, but they reproduce the one region of the image in another place of the same image. So our first pipeline is dedicated to identify what we call self-similar region in an image. And this is what we do. First, you have to identify where the PDF, where the images are in, for example, in a PDF file. Then you have to fragment every image into panels, because every figure contains more than one experiment. There are several panels very often. Then, for each panel, in each panel, you have to identify, let's say, interesting regions, like bends into a gel, or cells into a microscope image, or other interesting portion. These are called region of interest, ROE. And then you have to compare this region of interest one by one. So you align them and you see whether they are the same, so whether there was a duplication of a band, a duplication of a cell, or a duplication of some other feature in the image. And then you pass this to a human analyst to confirm or disprove a finding. And then there is another pipeline where you are interested in to see whether the entire image was reused, either in the same paper, for example, actin or tubulin controls or other kind of controls are reused several times in the same papers or even in different papers. So in this case, it's easier because you do exactly the same steps to isolate the panels, and then you simply compare panels. You look also, of course, for contrast difference, stretching, rotations, or other simple transformation of the panels. And in the end, in any case, you have a human analyst confirming your findings. In this case, for example, you see here on the left part, you see an image which was supposed to be the original material. If you use a special feature in a software which is called, in an open software which is called, which is called ImageA, you can show clearly that there is a region here which was passed in, okay? And this is only possible when a human analyst look into it. So the software can do very simple things, looking for self-similar region, looking for similar panels, stretching, rigid body motions and transformation, but very similar things. After that, a human analyst has still to look into it. So now the software is examining all the images that were in that particular directory, flagging some images where you see this red score. This is a gel in this case. This is the original image. You can select the feature here, like these two bands here, which were flagged to be the same, and then you can still go in further details, exporting these to Excel. You have these two bands in a pixel by pixel vision. Every cell in this Excel sheet represents the intensity of gray for that particular dot, and you have the difference, which happen to be very small. You see, these can range from 0 to 255. Every number here is between 0, 1, and 2. You can also examine these with usual stuff like ImageA, and for example, you can look to this image in false colors, which render your job easier because it codes difference in intensity as difference in colors. So it is easier to compare two features and discover they are identical. Once you find a potential issue in an image, I mean, you have to resort to some independent experts, which we do. We have some international help. and then you produce a report, and then this goes to the journal, and then this goes to the university and to the authors, and then, and in the end you have to wait for several years. So the average time for those papers who were retracted after our analysis, the average time we had to wait was 3 years. And this is only 1% of the papers we were able to get retracted. There is still one new thing we are looking at, which is about numbers. So this guy, this Bamford guy, identify a special distribution of the first digit if you have a table with several numbers, like for example an economic account, for example, you have several numbers, you can look to the first digit of each number which is in your account. These digits must follow a precise distribution which is called the Bamford law. The Bamford law states that, for example, if you have enough number and if you look to the first digit and there are no bias of some sort, then number 1 will be in 30% of your numbers, number 2 roughly in 17%, and so on. So if you have a table of number, for example, from a clinical trial, you can go there and look whether in first position again how many 3 you are, and so on. And in this case, the gray here is what you expect to find according to the Bamford law, and in this greenish color here is what we actually found in this particular clinical study. You see that people were fabricating numbers. For example, there is a large excess of 6 and of 8 in this table, which is simply due to the fact that they were either cherry-picking numbers or fabricating the numbers. You can also repeat the same reasoning for the second digit. The law is a little bit different. You see here you have in the same table you have a large excess in frequency for 3 and 4. And since you can download and process the table of millions of papers automatically, you can run this check for every paper having a table containing at least 50 numbers. And of course you have, in some case, these kind of deviations are expected because, for example, if you are looking to, I don't know, a table containing the age of patients of some condition which happened in elder people, then of course you will have more 6 at first position, 7 and 8 than expected. But these are special cases, and in any case won't affect the second digit of your distribution. And by doing so, we are starting to reanalysis the reanalysis first of several hundreds of clinical papers containing this kind of data, and we are starting to see a lot of surprise there. Okay, that's all. If you have any question, I'm here.